Hello and welcome to this lesson on catalysts. In today's lesson, we will firstly introduce the concept of catalysts and their role in altering the rate of chemical reactions, and then understand how catalysts work without undergoing permanent chemical changes themselves. So far, we've covered collision theory, understanding that increasing the number of collisions increases the reaction rate. You've also learned how factors such as temperature, pressure, and concentration can affect the rate of a reaction. Building on this foundation, today's lesson will expand our chemical knowledge by exploring how catalysts can speed up chemical reactions, helping us better understand the intricacies of reaction dynamics and efficiency. So far, we've explored how increasing collision frequency and energy influences reaction rates. But what if we want to speed up a reaction without changing conditions like temperature or pressure? This is where catalysts come into play. Catalysts are substances that alter the rate of a chemical reaction without being consumed or undergoing permanent chemical changes themselves. They offer an alternative route for the reaction that has a lower activation energy, allowing the reaction to proceed faster. To understand how catalysts work, we first need to recall the concept of activation energy. Activation energy is the minimum amount of energy required for a chemical reaction to occur. Without sufficient energy, the reactant molecules cannot overcome this barrier, and the reaction won't proceed. Think of a catalyst as a bridge over a valley. Without the bridge, catalyst, you need to hike all the way down into the valley and climb back up the other side, a high activation energy. With the bridge, the journey still requires energy, but it requires much less energy and becomes quicker and easier. Since catalysts offer a path with lower activation energy, more particles have enough energy to overcome the barrier, so more successful collisions happen, speeding up the reaction.
One of the remarkable features of catalysts is that they are not consumed in the reaction. They facilitate the reaction but remain unchanged and can be reused multiple times. This makes them highly efficient and cost-effective in various chemical processes. You may be wondering, why don't we add catalysts to all reactions then if they're so great? Each chemical reaction has its own unique mechanism and reactants, so the same catalyst cannot work for all reactions. A catalyst must interact with the reactants in a specific way to be effective, and the alternative pathway it provides must be compatible with this specific reaction. A catalyst suited for one reaction might not work for another.
Choosing the right catalyst depends on various factors. 1. Nature of reactants. Different chemicals interact differently with catalysts. 2. Desired products. The end products of the reaction can influence catalyst choice. 3. Reaction conditions, temperature, pressure, and other conditions affect how catalysts work. Catalysts play a critical role in industrial processes. Let's look at a few examples. 1. Platinum in catalytic converters. It's used to reduce harmful emissions in cars. Platinum specifically catalyzes reactions that convert toxic gases like carbon monoxide into less harmful substances. 2. Iron in the Haber process. This catalyst is critical for producing ammonia from nitrogen and hydrogen. Iron's properties make it suitable for facilitating the reaction under high pressure and temperature conditions. 3. Nickel in margarine production. Nickel is used to hydrogenate vegetable oils, turning them into margarine. Catalysts are also essential for life. We have biological catalysts or enzymes in our bodies. We will further explore this in the next lesson. As shown in the lesson, catalysts work by providing a reaction pathway that requires a lower activation energy. But how do catalysts actually provide this? Particles will only react if they collide in the correct orientation. Imagine trying to connect puzzle pieces together. They only fit together if they are correctly aligned. Even if particles collide with enough energy to react, if they aren't in the right orientation, new bonds will not be able to form between them. A catalyst provides a surface for reactants to gather on. The particles will be specifically aligned based on interactions between the particle and the catalyst. This holds the reactants in the right orientation for reaction. As more of the collisions are successful and lead to a reaction, the activation energy required is lowered. For example, in car engines, Catalytic converters align pollutants such as carbon monoxide by holding it on the surface of a metal such as platinum, so that they react more easily with oxygen to release less harmful gases such as CO2. In today's lesson, we delved into the concept of catalysts and their role in chemical reactions. Catalysts are substances that speed up reactions without being consumed or undergoing permanent changes. We learned that catalysts work by providing an alternative reaction pathway with a lower activation energy, which allows more reactant particles to have sufficient energy to react. This results in a faster reaction rate. We also learned that the effectiveness of a catalyst depends on its suitability for a specific reaction. We also looked at practical applications of catalysts in the real world. Overall, this lesson has provided a deeper understanding of how catalysts function and their importance in enhancing reaction efficiency in various chemical processes. Watch the rest of the GCSE chemistry course at Sophos Education.